Okay, so I'll start now. Okay, so this is going to be very straight and staid kind of stuff, not very much play, but what I'll do is, I'll give you some results on the fixation probability of a beneficial mutant. And by now, you know that fixation probabilities are an essential building block of stochastic models, so we need to know them. Okay, so I'll do this for a couple of models. I'll just describe basic results. And my emphasis here today is on the case when deleterious effects are weak. So what I mean by that, let me explain. Okay, so here is just a little cartoon just to remind you what we mean by fixation probability. So I just have a finite population of size, say, 5 initially, and there's a beneficial mutant which appears, and it goes through selection, mutation, genetic drift, etc., etc. And I'm going to assume today everything is asexual. So it goes through selection, mutation, and drift, and at the end of the day, maybe all the organisms, all the individuals carry this beneficial mutation. This can happen, but because of stochastic fluctuations, none of the individual carries it. That means beneficial mutation is lost. And we are interested in asking what's the probability that this beneficial mutant is eventually fixed. So this is a standard question in the subject. Okay, so I consider two different models. So let me first explain a simpler model, which is a very standard model in the literature. And there has been a lot of numerical work, but I'll give you some simple analytical results. So that's where that's what my goal is. Okay, so the model is the following. I'm thinking of a large but finite population of asexuals. And again, I assume that each individual is specified by a binary genome, and this genome is infinitely long. So the standard assumptions that we already heard in the previous talks. In here, only deleterious mutations occur to begin with at a rate UD, and every deleterious mutation reduces the fitness by a factor 1 minus ST. Okay, so let's begin with the simple thing first. Okay, so in this population, if the population I'm assuming is very large, to begin with, I can just ignore the drift. So what will happen in this population? Mutations are deleterious, so they will tend to lower the fitness, but such bad mutants will not be selected, right? So deleterious mutations will lower the fitness, and selection will try to oppose it. So there is a mutation selection balance that is reached, and this is a classic result in the subject, that there's a frequency of the population with k deleterious mutations is simply given by this ratio, UD by ST. So this is an important number, important parameter in this talk. Okay, so the average number of deleterious mutations is simply the ratio of mutation rate to the selection coefficient. And I can plot these frequencies. So for low mutation rates, the frequency is centered about low k, and as UD increases, it shifts rightwards. Okay, so far this is all standard classic deterministic answers. Okay, so now I imagine that in this large population in which there were only deleterious mutations, one beneficial mutation occurs at a rate UB, and that increases the fitness by a factor 1 plus SP. And I'm just asking the simple standard question that because of fluctuations, this rare beneficial mutation can get lost. What's the chance that it eventually fixes? Okay. So a lot is known, almost everything is known in the case when these deleterious effects are strong. And let me say what I mean by strong here is that the effect SD is much, much larger than SB. So practically everything is known here, but let me just take you through it so that you can contrast it with the results that I'm going to give you. So the first thing that you have is the classic result of Haldane. That is that if there are no, if you're in this parameter regime and there are no deleterious mutation rate is 0, then the p-fix is twice the fitness advantage, twice the beneficial fitness effect. So that's you have seen several times in the last few days, right? Okay. But now let's allow deleterious mutations to occur and they have this strong effect. Then what would happen? So let's just imagine that for a second. So now every mutation lowers the fitness substantially. And now a beneficial mutation is also occurring. Then it has a chance to survive only if it occurs in those individuals that have no deleterious mutations. That is, the survival would is substantial or it's reasonable, it's relevant only if the mutation arrives in just one background. So that's the key point here. Okay? So when I have strong effects, then fixation is possible only if the beneficial mutation arises in a background with no deleterious mutations. And I know the frequency of them. I just gave you in the previous slide. There's a formula for this, so I just wrote that. Okay? So we have a simple expression that the fixation probability when the deleterious effects are strong is simply the previous answers, and it's reduced by this factor e to the power minus ud by st. So this is all standard known answers. Okay, let me just go a little bit ahead. So just like I said, that as you expect that deleterious mutations would reduce the fixation probability, and that's what it happens. It's an exponential function. And note that p fixed by 2sb is independent of sp. It's not dependent on the effect of the beneficial fitness effect. Okay, so fine. So let me just tell you one more known result. So again, you heard already that it can happen that while one beneficial mutation is going to fixation, the one that I'm looking at, better ones, that means which have a higher effect, they could also arise and impede the fixation of the one that I'm looking at. And that's called the clonal interference. And so again, one can calculate how much is that lowering of the fixation probability. So the black curve is without this clonal interference, and there's a lowering with the clonal interference. Okay. So this is now dependent on the population size. Yeah, so there is some n. I took so much that Malus-Ratchet doesn't occur, it's very slow. Yeah. So this is for a particular n. This curve, red curve, orange curve. Okay. Yeah. Okay. So I'm interested in the case when deleterious effects are weak. That's the new part now. So here, let me repeat. I'm interested in the case when ST is much more smaller than SP. So let's see what is different from the previous case. So I told you that when the effect of the deleterious mutation is large, then if I take a step, it just fall down because, you know, I become my fitness lowers a lot. So I better be in a background where there are no deleterious mutations. But now it's the opposite case. So, you know, I can survive in many backgrounds. So that's the big difference that happens in this parameter regime. So now the beneficial mutation can survive in many backgrounds, and the number of backgrounds is a second important parameter here. It turns out to be simply the ratio of these two selection coefficients. Okay, so these are the just two parameters I want you to remember. K bar equal to ud by st, and there's a k max, which will depend very model to model. Okay, okay, fine. So we have these two numbers, and there are lots of backgrounds. K max is very large in the parameter of regime of interest. But not all backgrounds are important. What are the backgrounds that are important? Are the ones that, so you see, so survival can happen in many backgrounds, but this beneficial mutation is likely to arrive in a smaller subset of backgrounds. It's simply the ones which are in a standard deviation about the mean. Okay, so that's because of this f of k, the population frequency, which is a Poisson distribution. Let me just show you a curve here and repeat what I was saying. So I'm saying again that the survival could happen in many backgrounds, in this k max backgrounds, that's the black curve. But the red curve is in which background does the beneficial mutation arrive. So if UD is large, then it could be, you know, it's a broad distribution like this, and otherwise it's a narrow one. So now I can think of two cases here. If K max is much smaller than K bar, the overlap between survival and arrival is negligible, and you expect P fixed to be 0. Right? Make sense? On the other hand, if K max is much larger than the width, that means K bar minus K max minus K bar is within a standard deviation, then you expect the answers to be more or less like the single background case. So you expect P fixed to be like 2sp. Right? So these are the two limiting cases. So what I'm saying here is that if I increase the deleterious mutation rates, P fix will go from 2sb to 0. Right? That's a simple expectation mathematically as well as intuitively. Right? So that's what, I mean, one gets, of course. So there are these two curves, which I'll explain where I got them from, and there's a certain shape for it. And the question is, what is this shape? Okay. So like I said already, it's going almost, this relative probability almost from 1 to 0. Okay. So let me just take a small corollary from what I just said. So if I just convert this k max and k bar in terms of the parameters UD, SD, SP, then it looks like this. So it's saying that, okay, so let me repeat. Okay, so there is this distribution which is going from 1 to 0. It has a certain width, that is, its non-trivial values, that is between 1 and 0, in a certain width of this UD by SP. So it turns out that this width decreases with decreasing deleterious effect. That is, when ST goes to 0, P fixed goes to, there's a sharp transition in the fixation probability. So let me repeat what I'm saying here. I'm saying when the effect of deleterious mutation is negligible, then the fixation probability jumps from almost 1, that is the relative one, from almost 1 to almost 0. It's a sharp transition. So this has been seen in other contexts also, but and numerically as well, it has been observed, and here using my calculations, I find the same answer. Okay. So what are these points that I'm showing you? So I showed you this sort of two graphs. There's a black curve and the orange curve, right? Okay. So what are these points coming from? So I just wanted to spend just 2 minutes on saying where is this calculation from. So basically, this is the branching process calculation. I start with a standard multi-type branching process and write out everything. It's a very complicated equation and not really very useful. So what I do is simply to make a quadratic approximation, because it's the same level as the standard Haldane approximation, which gives you 2s. So that's all I do. So when I do that, then I write down the probability that the fixation occurs when background has k deleterious mutations. This equation, the scaled one, it's a nonlinear, it's a square term, and it's k and k plus 1, and the coefficients are k dependent and so on. So this is a non-trivial equation, and as far as I know, there's no exact solution. However, what I have been able to do is to find an approximate solution for this, and it works particularly well when ST is less than UD. So it has this linear term in k and a double exponential term. Okay, so this is sort of basic technical progress, if you like, that I have been able to make. So just to show you how does it look. So the black points are, sorry, the orange points are obtained by iterating these things numerically. There's a linear part, and there's this funny bumpy thing, which is the double exponential part. And the orange points are obtained by doing this calculation. Okay, so that's the sort of comparison, and I think it's pretty good. Okay, fine. So basically, those points that I showed you earlier. Yeah, so this again, the orange ones are from numerical iteration, and the black ones are I do some integration, etc., etc. And the expression is rather long, but it's possible to get this expression. So that's the basic point I wanted to make here. Okay, so one could also try this with clonal interference, and I just tell you some preliminary results because only a part of it I'm able to understand right now. So if I allow for clonal interference, then I find that the scaled fixation probability is okay. So when few backgrounds are relevant, then the clonal interference reduces the fixation probability substantially. There's a large variation amongst themselves, also with respect to each other. But when many backgrounds are relevant, then there seems to be rather a constant drop. So this case, I have some understanding, but this is something I still don't have a quantitative understanding of. So, yeah. Yeah.
Clonal interference. Clonal interference, I used to think of it as two beneficial mutations.
Yes, but so I'm saying here that I have a distribution of effects,
right,
and they are chosen, let's say, from exponential distribution. And while this one is, I'm looking at this guy with a certain, effect. Well, that's going to fixation. Other ones, better ones, could arise and impede.
Then it depends whether they arise or not depends on the size of the population.
Yes, this is all the simulations. Everything is in a finite population.
Okay, but it does. I mean, it comes in as a parameter.
Yes, yeah, so I didn't mention n, but there is a n which is large enough so that Muller's ratchet doesn't click. There is an n, it does depend on n, the population size, so which I didn't mention here, but it's large enough that I can assume that the population is at approximately mutation selection equilibrium. Yes, that's my resident population. Okay, it's a standard Lenski Gerrish calculation is just that. I haven't done anything, I have just plugged in my fixation probability expression, that's all. Okay, and I checked numerically also, and I think it works fine. Okay. Okay, so that's all I wanted to say for the case when I have a direct selection. And I just wanted to emphasize that there has been this question, it's been there for several years. I think one of the first studies has been in 95 or so, but again numerical. But so we have been able to get some analytical answers for that. How much far it can be pushed, I mean, that one has to see a bit more carefully. Okay, so let me just go to the second problem, which is, again, the resident population is very similar to what I had earlier. Again, I have a large asexual population at mutation selection equilibrium. Deleterious mutations occur at a rate UD. Each mutation decreases fitness by factor 1 minus SD, just like I said before. But now, the invader is a non-mutator. That is, it has just a mutation rate which is lower than that of the resident. That also goes only through deleterious mutations and reduces the fitness by factor 1 minus SD. Yeah. Resident means this large population which is sitting at mutation selection equilibrium, and then a certain special mutation occurs. This is the invader. Okay, so here I say indirect selection because I'm considering only deleterious mutations, and you expect lower mutation rate should be favored. So in that sense, this is indirectly selected. And one could ask the same question, what's the chance that this will fix? So there has been a lot of work in the opposite case, in which the population is evolving, is adapting, and then what's the chance of mutator fixation? In contrast here, I'm considering adapted population, and I'm asking what's the chance that a non-mutator fixes? So this is as a complement of the other situation. Okay, so here also the results are known when the deleterious effects are strong, and by that I mean here that ST is much more charged than EUD. Again, if a deleterious mutation occurs, it reduces fitness a lot. So in that case, basically you can work with the single locus results, and these are the standard results here. This again twice the fitness advantage. What that means here is simply the difference between the two mutation rates. So that's again known. And then there's also some other arguments saying that how this relates to the evolution of mutation rates. The idea here is that if the mutation rate is certain value, U, in a finite population, and a mutation occurs which lowers the mutation rate, it will get fixed, but this will keep evolving, and the fitness advantage by lowering the mutation rate will keep getting lowered till it reaches a mutant limit. And that, coupled with this results, gives you a relationship between the mutation rate and population size that U is roughly like 1 by N. Okay? So larger populations have smaller mutation rates. So this is the sort of stuff which is done by Lynch and others. Okay, so so I can just repeat the same math that I just sort of briefly described. The difference here in this situation compared to a direct selection case is K bar is same. So I said there are two parameters only, K max and K bar. K max is different here. It's simply the difference between the two mutation rates divided by selection coefficient. So in this case, K max is always smaller than K bar. That's the difference from the previous situation. So earlier I was drawing the frequency here as well as here, but now it's always the set. That's the only difference. But that makes a difference in the behavior of P fix. Because you see, if K max is much smaller, if this guy is much smaller than K bar, then hardly any overlap, and you expect P fix to be 0. In the opposite limit also, that is when K max is larger, because it's bounded above, there's really no room, I mean there's very little room there for the overlap. So therefore P fix again becomes 0. So I'm saying that if I increase, as I increase the deleterious mutation rate, I expect fixation probability to be a non-monotonic function. So that's the sort of upshot of this little diagram. Okay. So, and one could calculate and get some factors, etc. So this is what the fixation probability looks like. It's a non-monotonic function. Okay. And sort of physically to think about that. So if I'm saying that if the deleterious mutation rate is high, UD is very high, and a non-mutator fixes, the background is so bad that non-mutator doesn't really help much. It doesn't have enough advantage. So the chances of its fixation are small. So that makes sense here. On the other hand, if the resident population, the resident mutation rate is low, and again a non-mutator arises, the mutator is not really suffering all that much. It doesn't carry so much mutational load. So non-mutator again doesn't offer enough advantage, and again I expect fixation probability to be low. Okay, so the point I'm making here is that there is a maximum here, and that maximum, so you can do a long calculation or just this little argument, and if I convert all this into the factors here, UD, SD, etc., what that means is that this maximum occurs when UD is of the order of lambda square SD. Lambda square is the ratio of the two mutation rates. That's the main point here. Okay, there is a critical, the most likely scenario is when lambda, that is the strength of the mutator is of the order of this, when this number is order 1. Okay, so let me just say quickly what this means. So I'll just give you a couple of applications of these results. So, so like I said already, non-mutator of strength lambda proportional to square root of UD by SD is most likely to fix according to these calculations. So this was motivated, this question was motivated by Lenski's experiment in which mutation rate rose by a factor, by 2 orders of magnitude when the population was adapting, but then it decreased only by a factor 2. So there was this, just in 2 lineages, it reduced by a factor 2. And I just wanted to understand why 2, why didn't it reduce back to factor by 100 factor? So if you put in these numbers here from Lenski experiment, so UD is 0.03, lambda is 2, so we get a reasonable value of SD. So what I'm saying is here that this sort of calculation is consistent with the Lenski experiment. In general, if I take SD to be weak, like 10 to the minus 4, 10 to the minus 2, and high mutation rates, lambda is small, it's like 10 or so. Okay, so this, if you like, is a simple population genetic explanation for the fixation of non-mutators which have a lower, whose strength is rather low. Okay. Other thing I wanted to point out is we could again look at Lynch's drift barrier argument, and like I said earlier, if deleterious effects are strong, then U is proportional to inverse of n. This calculation, more detailed calculation shows there is a parameter regime when it decreases faster, like n to the power minus 2. But it's not so much about whether it's n to the power minus 1 or n to the power minus 2. What I want to point out here is that this mutation rates also depend on the selection coefficient. And all the data that Lynch has collected and collaborators, somehow there's no mention of what happened to selection. There is a reciprocal relationship, I mean there's an inverse relationship, and there's data from humans to mouse and everybody, but there's no mention of selection at all. So we think that it should figure, but I mean, I'm not sure how, what one can do here. Okay, so that was all that I wanted to say today. So I hope I gave you some results that go beyond the canonical 2S type of results, but there are still questions that I would like to address, which is sort of in the works. That's all I wanted to say today.
Okay. For all of these, this is an infinite sites model. And one of the questions that I have is what happens if you actually try to, I mean, maybe just numerically, look at this for a finite genome size?
Yeah, so first of all, I'll have to worry about, okay, so resident population I know enough about, even if I have finite size. It should be possible, I don't know how it will change, but I think it should be possible to do that, even analytically. But I don't know how it would change the answers very much. So, I mean, I guess you're worried whether there's a back mutation. Is that the point? Yeah, yeah. Yeah, so I think there are, not my study, but other studies in which they actually take care of the beneficial mutations, beneficial mutation rates also, and that changes things. So I think this is Snigowski et al. Has done some recent study. So that makes a difference, yeah, beyond a certain population size.
You mean that's, I guess I was going to ask, in the Lenski experiment that's proposing data from, the Lenski experiment, the population is still considered full. And so how applicable is it?
Yeah, so but this is like after 30, 40, 50,000 generations, when this non-mutator, the lowering has happened at 50,000 generations, so it's evolving, but very slowly. So I think as a zeroth order approximation, mutation selection equilibrium should be fine.
But then there's one has to ask rather explicitly as to how big the beneficial mutations are coming.
We did have a small study when we allow beneficial mutations to occur, but we couldn't make really much sense of that. I mean, this numerically we did a bit, but it didn't make much of a difference. But maybe we didn't put enough of that, so I'm not so sure. Yeah, but that's like the first limit, because it's just two backgrounds are important. So it's like the SD by SB is 1. So that we can basically do it exactly.
Okay.
That's not it doesn't make much difference. It's not, I think, not very important, I think. No, so everything is in equilibrium. That is, things are settled down, and then this guy arrives, and I'm asking what's the chance that it eventually fixes. One can fix it, put in time. So this equation, it's not difficult to generalize, but right now I don't have a strong motivation to do that. So these equations, one could write it in time, and differential equations, etc. It should be possible. One could put in time. It's not, I think it's not very difficult, but I'm not sure if that's going to be useful. Right. Yeah, so yeah, that would change with time, but then actually one should start with a population which is not in equilibrium. The resident is changing, and then this guy is coming and his fixation might change. So that's the sort of situation one would look at, but I don't know what's a good point to, good situation to start with. Right. So basically the thing that I wanted to address is because it's been questioned within there, the literature 15, 20 years, so I thought I'd show it to you that we have some answers. Okay? Yeah.
So how did you simulate in these cases? Like, which process did you consider?
The usual Wright-Fisher.
But why like Wright-Fisher? I mean, like, what was the motivation? I mean, why not Moran process?
You can do that. It'll just make a 2 or 4 difference.
Okay, so
But
basically it won't make any difference.
With discrete time process.
Okay.
Okay. Thank you.